In this video, I'm going to discuss and introduce magnetism, and we're going to start with magnetic poles and magnetic field. Magnetism. Magnetism. Magnetic force applies, you have a magnetic force when you have magnetic, the source of, let me just say it, magnetism. So the source of magnetic force is magnetic poles. Magnetic poles. And the magnetic forces look very similar to electric charge. So you have for electric charge, you have a positive and negative, two polarities. Magnetic poles also have two poles. One is north-seeking pole. I should say north-seeking pole. And south-seeking pole. And very similar to electric force, magnetic force, when you have such as north and north, so N and N, like charge, like poles, N and N, or S and S. So when you have like poles, they repel. The force is they repel. And unlike poles, the combination north and south. So when you have unlike poles, they attract. Here's a video. So there's a bar magnet. So here's the bar magnet, and it has a north and south, two different poles. I have another one here. And like poles, repels. They don't like each other, right? North and north. And what happens? Unlike poles, north and south, beep, 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 sticks, attract. So, as you saw, north and north, like poles repel, unlike poles attract. So it's very similar to electric force. What is different is that though, that unlike electric charge, that you could have just one electrons or two electron, just have one negative charge, which is called monopole. The difference is that magnetic poles always in pair, which means that you're never going to see just the north by itself or south by itself. If you can find the magnetic monopoles, you can get a Nobel Prize. So when you have a, let's say, bar magnet or anything, let's say you have a magnet here, right? And then one end is north, the other end is the south, and an S. Let's see, if I were to cut this into smaller piece, I'm gonna cut it. Still, what happens is that one end becomes north and south, north and south. If I cut it even smaller, smaller and smaller and smaller, no matter how small I cut it, it always comes as a pair. Always. Always. You're never going to find the one just by itself. So that's very different from electric charge. But otherwise, the magnetic force exerted on magnetic poles, and it also obeys 1 over d square. It depends on the distance of two poles apart, square, inverse, square. So it's very similar to those magnetic force, which means that magnetic force is also a field force, and you can see there is magnetic fields. Little preview. Magnetism is just a preview is that magnetism. So I said that magnetism is from these magnetic poles, but it's due to the motion of electric charge. So this is just a preview. Okay, so let's now talk about magnetic field. Magnetic force obeys 1 over d square. In fact, that a magnetic force looks like a P1, P2 over d square, where P is magnetic pole. So stronger magnetic pole, of course, you're going to have a bigger magnetic force. Applies Newton's third law that applies on one magnet to the another. It's going to be equal in the opposite direction. So something like that. D is the distance square. So magnetic force is very similar, and then it's a field force. Non-contact force, it's a field force. So therefore, you have a magnetic field. And conventionally, magnetic field, so you're always going to have a north and south, right? North and south. Conventionally, magnetic field lines you can draw out from north seeking pole into south seeking pole. Out from north seeking pole into south seeking pole. Similar, it's never discontinuous. Magnetic field lines. From north to south. That's how you do the arrow. And then the denser lines means stronger magnetic field. Very similar to those electric field. And doesn't cross. Or continues indefinitely. It's because of this 1 over d square. So even though you go infinite, it becomes very small, approaches extremely close to zero, but it never becomes zero. So the line will continue out if it goes out. So it's very similar to electric field. And I'm pretty sure you might have played with this kind of a stuff. You have a magnet and then you put it close to the iron bits. So here it's iron bits. I'm not saying any old metal, okay? So Avery, what do you have in your hand again?
Baby oil with some little stuff in it.
The little stuff are iron bits. Can you say?
Iron bits.
Iron bits. And then what's this?
A magnet.
This is bar magnets. All right, let's see. Here we have a white sheet. Can you put the magnet on the white sheet, please? Place it there. Yeah, thank you. Gesundheit, Ichan.
So when you put
I'm a
this
little concerned about this, but
this,
you
do
see?
you see? There's little iron bits and it looks like hair.
They're making a hair. Yeah. This is so irons without the magnet bars, they're just pieces of iron. But when they're close to the magnetic field, it aligns along the magnetic field. So we see these magnetic field lines. That's why each of iron bits are aligning along the magnetic field. So that's it. These iron bits that's in a baby oil. I use the baby oil so it's a little more viscous. But then without the magnets nearby, they're just the regular iron bits just in oil. And then you put magnets nearby. Then those iron bits aligns with the magnetic field that's being generated by the those bar magnet. So that's what we see, and yeah, that's it for the magnetic field. We'll talk a little bit more what is causing magnetism in the next video.